Welcome back, everyone. This afternoon, we delved into the fascinating realm of space and astrophysical plasma, a domain where theory meets cosmic reality, chaired by Dr. Amit Shukla, IIT Indore. This session will explore both research and emerging simulation in plasma astrophysics. So now, I request to Dr. Amit Shukla, please come on the stage and session the chair.
Thank you very much. So I welcome you all in the session which is based on space and astrophysics plasma, and our first plenary talk will be given by Professor Durgesh Tripathi. Professor Tripathi is a distinguished scientist and a senior professor at IUCAA, Pune. He is the main principal investigator of our first Aditya L1 payload telescope, and the payload is Solar Ultraviolet Imaging Telescope suite, and he has earned his PhD from Max Planck Institute, Germany, and he has done several postdocs at Cambridge University and other places, and he has also earned one of the very famous honor fellowship, Hall Fellowship. And with this introduction, I will invite Professor Tripathi to give the plenary talk.
Okay, good afternoon. Thank you, Amit, for the introduction. And I would like to thank the organizers to invite me to give this talk, and in particular to Nishant and Bhargav. After lunch, you keep the names go missing. Anyway, so today I thought I'll share with you the excitement of observing any object in the sky using an instrument that you have developed. This talk is technically challenged in the sense that, in the morning you saw a lot of equations and a lot of things going on in there. That way, this talk is not going to show any equation whatsoever. It will show you some pictures and I think there are movies, but they're all observations taken not only by our instrument, but also from outside, and then you combine. So this talk is nothing more but an invitation to you to come and use the data, not only for doing science, but also to explore what the sun looks like in near ultraviolet and how sun evolves, because at the end of the day, this is your nearest star, which, of course, you can use it for understanding other astrophysical bodies, but also you can use it as the nearest natural plasma physics laboratory. So with that, I'll start by showing you this curve, which essentially is the irradiance that you measure above the Earth's atmosphere. What kind of radiation you get from the sun. And what you see here, we are going from extreme ultraviolet all the way to the IR. That dashed line is the irradiance map that you would get if you were measuring the solar irradiance at the sea level. And that is why you see all these absorption lines coming in, and those are essentially because of your water molecules. So that tells you that this vertical dotted or dashed line, below which, if you want to observe, then you have to go to space, and beyond that, you can do that from ground. Now, we all know that where does the visible emission comes from, and that comes from the photosphere that essentially is coming from the gamma ray radiation, which is happening at the core of the sun. Those gamma ray photons are essentially traveling through the interior, losing their energy, becoming white light photons, and they're coming to you. What we don't know that where exactly these photons, which are ultraviolet and extreme ultraviolet, they are coming in. And it was to figure out essentially that if you need to have those photons coming from the sun, then the atmosphere of the sun would have to be hotter than the surface of the sun, right? So you probably all know surface of the sun is around 6,000 degrees. That's where you can fit that, the visible curve with a black body curve of 6,000 degrees, and you will get that. But then that does not explain your ultraviolet and extreme ultraviolet and X-ray emission and so on. So by looking at all this and doing other measurements, what we know now is that the sun's atmosphere is structured, and you don't only have the surface, which is the T-min that is plotted over here, the 0 to 500 kilometers or so on. That's the surface thickness. That's the photosphere. That is where most of the visible light photons, they come out. But you also have other layers defined. So the solid line there is the temperature as you go out into the solar atmosphere. So when you're going further out, of course, you have the temperature minimum. That's what you expect, that you can go from away from the ball. You will hit a minimum. And then slowly in the atmosphere, the temperature starts increasing. It gets to a plateau and then suddenly increases from about 20,000 degrees to 1,000,000 degrees in that transition region, and then goes to about 1,000,000 degrees and more, defining the solar corona. And because of that temperature enhancement that radiates in this high energy radiation are high energy photons, which are your ultraviolet and extreme ultraviolet. Now, the question has been that we know that, of course, the sun center is hot, you have the nuclear fusion going on. We don't really know that what happens that the atmosphere becomes hotter and then eventually produces those kind of radiation. And that is, if I may say, one of the most challenging problems since its discovery in the 1960s. Now, because we know that this is happening and it is nearby object, we can define filters. Now, defining filter doesn't mean that only you can do it for nearby, you can also do it for far away. But what you can also do, not look at the static observations like once in a day and so on, but you can, because it's nearby, it gives a lot of photons, you can collect them fast enough. You can define instruments in such a way that you can also look at the dynamics at the time scales as low as we can get, and with our instrument we can get up to about 4 seconds. Every 4 seconds we can take an image of the sun in one of the filter, and we can see how things are evolving. But when we do this, like let's say we can define our filters at different height, which are like sensitive to different frequency of photons, we can map the atmosphere of the sun. And if you do that by combining ground-based as well as the space-based observations, what you would see is the bottom left is your good old sun, the orange color that you see in the morning, that you can do it from ground. The second image here from the left is the magnetic field mapping, which I'll come to. But you can define these filters. For example, you're looking at ultraviolet at 1600 angstrom, then H-alpha, that you can do from ground, and so on. You can go all the way up to X-rays. And what you find is that depending on the wavelength or the frequency you are looking at, the sun's face is very different. However, one thing is very common, and that is that if you look at, that is where I would have needed a pointer. If you look at this region here, now I see all pixels here because I'm so close. You see these dark regions, which are the sunspots, right? The sun signal is so good that I can do a spectropolarimetry, and I can measure magnetic field at each point on the sun. Not only the strength of the magnetic field, but I can also do the polarization measurement, and I can get the direction of the magnetic field. In this map here, we only show the longitudinal, that is the line of sight magnetic field, or the field coming towards you. So the white shows the north field, that is the field is coming towards you, and the black shows the dark, which is the field going inside, right? Now, if you compare these, of course, we know the sunspots are the highly magnetic regions, and that's what you see. The color here shows the strength. So the darker the sunspot is, stronger the magnetic field is over there. But what you also see, combining that, wherever you have the stronger field, the high energy radiation is larger in those regions. And if you go all the way to X-ray, that you see that is very nicely correlate that it's only in the strong field region you start seeing X-ray. Otherwise, X-ray is quite minimal. What you also see that there seem to be some characteristic temperature of the upper atmosphere, which is around 2 million degrees, where not only the bright features where the strong field is there, but you also have all these structures which are appearing and giving you a kind of background corona of the sun. When we measure these magnetic field now, we find that, of course, the sunspot regions are the stronger field region, but the sun is full of magnetic field like salt and pepper. And that will then give you a picture of that if you take this surface and you have the magnetic field distributed and you draw lines of forces, right? You can do that in different approximations like potential field and non-potential field and so on. What you then imagine is that the atmosphere of the sun is full of magnetic loops, which are arcades. And when you fill the plasma in those loops, they brighten up. And that is what you see in all these images at the high temperature. The question is that how do you fill those flux tubes, if you like, with those high temperature plasma, which are essentially emitting at these wavelengths. Now, all physicists, they go for extremes. So, in the solar atmosphere in last 30, 40 years, 50 years, have been devoted to define space missions in such a way that you look at the extreme environment, like transition engine, the corona, thinking that if you have the ground-based measurement and if you're looking at the top, you would be able to connect and understand that how things are. It turns out that's not the case. We have so many data points over there, but only about 2 data points in this 1,000 kilometer regime in the photosphere and chromosphere. But the magnetic field, which is generated deep inside the sun through a dynamo, has to pass through the photosphere and chromosphere, get into the corona. You have to look at the dynamics of the magnetic field in different plasma environment to essentially look at the coupled system in that way. And why magnetic field? Because since the magnetic field is very nicely correlated with all these bright features you're seeing in the upper layer of the atmosphere, while we did not know earlier what the source would be, now we know that the source has to be magnetic field. It's just that what we need to look at, the transport of energy from one layer to the other layer via magnetic field. That's one question. And the second is then how, even if the magnetic field is carrying this energy, how does it dissipate and eventually hits the plasma? And therefore, you need to understand these regions as well and look into combination of this. Now, the problem is that depending on, if you look at this density and temperature curve here, the parameters change so much when you go from photosphere all the way into the corona. Theoreticians don't like it when we say that you have to look into the coupled system, because the physics they have to deal with in the lower atmosphere is very, very different than the physics they have to deal with the upper atmosphere, right? But that's life, and we have to do it, and we have to deal with it. Okay, now, let's define this heating problem a little bit more further. I showed you this. You must have heard about, for example, solar cycle, which is 11 years. So because we can do it every second, every 4 seconds and so on, we can also do it every 1 year and so on. So we can build a statistics, and what we find that the sun's magnetic cycle is 11 years long. And depending on how the magnetic field is modulated over that 11 year, that is how the high temperature emission from the atmosphere is also modulated. And that gives another further constraint that the magnetic field has to define what the upper atmosphere has to do. So here you see the solar maximum when you have a strong magnetic field region, a lot of them, a large scale field. You see also a lot of X-ray emission. And when in the solar minimum, when the sun's disk looks almost flat, you have almost little to tiny and almost no X-ray emission. Now, we talked about how and where the mass and energy has to come from, and let's get into that detail a little bit further. Now, so if you quantify, if you take this X-ray, one image of the sun, you have different regions. You have the strong field region and the weak field region. There is something called the active regions where you have the sunspots and very strong field. There is something called the background corona, which we call quiet sun. And then you also have these dark regions. They are not essentially a hole in the sun as such, but the intensity is just low because we know that when you do the magnetic field modeling, the magnetic field lines are essentially open into the interplanetary medium. Now, opening means the del dot B equal to 0 is not violated, it's just essentially coming up and connecting to the southern pole of the sun. But the intensity is lower because it finds a way, the plasma finds a way to go into the interplanetary medium due to this large scale field producing solar wind. Now, if you look at the total energy required, for example, so if you take this active region, work out how much is the total energy loss, right? What we find is about 10 to the power 7 ergs per centimeter squared per second. If you go to quiet sun region and the coronal hill region, both, you find it's about 10 to the power 5 ergs per centimeter squared per second. Now, these active regions, let's say, and the quiet sun is always there on the sun, are losing that much amount of energy. So our heating problem has been reduced to the fact that if anything is losing that amount of energy per unit time, then you need to pump that much of energy to keep that thing alive, right? And if the time scale for these features are about a month, sometimes 2 to 3 solar rotations, which is one rotation is 27 days, then you need to keep pumping energy to keep things alive, and therefore corona has to live, and therefore the energy and mass has to come. Now, where does it come from? As you can see, the quiet sun is your background corona, let's say, for the moment. The density is lower, that's why the emission measure is lower, and you see less emission. So the mass has to come from the region where the density is larger, and that is your chromosphere. Look at this dashed curve. So the magnetic field is coming in, going into the corona. You have to fill this tube to make it brighter, but the reservoir of mass is at the foot point. So you have to make the mass from the foot point go up into the corona. And we observe all this, that how the mass is flowing. We see in many things that the mass is flowing, but it's not a completely consensus thing that you can see it every time the same thing happening to reach to a consensual theory. And that is why you have to, again, look into the coupled system. Now, sometimes sun also produce these large-scale eruptions. And one of those we call flares. And just before lunch, we were talking about magnetic reconnection processes. We know that that takes place. And we have observed that in flares. So this is one of the examples. That's Bastille Day flare in the year 2002, I think. What you see there is 3 images taken simultaneously from 3 filters and put together in 3 colors. The temperature, the maximum can go there up to about 20 million degrees. What happens earlier is like you see sometimes flare also like this, depending on the wavelength you're looking at. When you look in the same flare or similar kind of flare in H alpha in the chromosphere, you see these kind of ribbons. And if that movie works, that will show you how the magnetic field lines are coming and pinching together. It doesn't work. Yeah, so you see that guy is going up, and then the field lines from outside, they're just coming and pinching and letting the mass go. Now, how this all is connected? So the way we understand it is like you have this system in the bottom right panel, which is sitting, so you have a mass sitting there, which is of course supported by magnetic field, and you have these overlying fields. When the system gets into a stage that it cannot hold anymore, it could be because of twisting and tangling, because you keep twisting a rubber band, eventually it will go through MSD instability. Then you will keep rising this, and to keep it rising, you have the magnetic reconnection from the loops, which are outside, they be pinched inside to reconnect, to push the plasma away, which will give you a mass ejection into the interplanetary medium. But when the reconnection is happening at the foot point, what is at the top, what is happening? You are releasing that magnetic energy, transferring it into thermal energy as well as particles. Now, those particles, they have to travel along the field lines. So if you have something, reconnection happening on the top there, you have these outer field lines. Those particles, they carry energy, and then they travel towards the foot point of the magnetic field. And what happens? These energetic particles are accelerated. They are going and hitting a rock bottom, which is very high density chromosphere. Depending on how impulsive these deposition of heat is happening, the chromosphere responds very differently. It's a high density, so everything is Bremsstrahlung. It will go at any square lambda t, right? So if you do it very gently, then it will be happily radiating and staying there. But if you do it very impulsively, then the plasma gets unstable and it starts evaporating, right? And that is what then will go, and that will have to happen impulsive at a very high temperature. It will start going and filling the loops, and that is what those loops you see in X-ray. And when these loops, then the plasma has to cool down, so it will cool and the plasma will flow towards the foot point again. It will appear into different subsequent channels. So if you make it a spectra, then it will go from high temperature to lower temperature to lower temperature. These happens all in flares. And flares in the very early days were considered to be one of the ways to heat the solar corona to make the plasma always as a million degree. Because here, temperature can go up to about 20 million degrees. But the numbers of flares are so infrequent of these kind of flares that people consider that it's not enough to explain the total energy budget. But then, since the magnetic field is everywhere on the surface, you don't have to have always these kind of large-scale eruptions. It can happen always at very tiny scales, which you'll have to observe, go into very high-resolution observations, and trying to figure out that if that number is enough, if that energy is sufficient to solve. And that is what is one of the goals to actually look at where and how these tiny depositions of heat happening and how the plasma, the chromospheric plasma is responding. Now, in addition to all this, you also have this near ultraviolet. When the high energy radiations from the sun, they come to the earth, they do different things, right? The radiation is, the high energy gets absorbed. The X-ray and extreme ultraviolet, they are absorbed higher up. But the near ultraviolet comes all the way into the stratosphere. Now, when these energy, and they change as a function of solar cycle at with a time scale of 11 years, the Earth's atmosphere also starts to get heated up and cool down at 11 years, so it would have a lot of space weather effects. What we know that the total energy, if you add up all the way to infrared from X-ray, that doesn't change over a solar cycle by more than 0.1%. But it's the high energy one below 400, that is what you have to go to space to observe, that changes from solar minimum to solar maximum by more than 60%. And that is what then creates the problem into space weather and also space climate. The near ultraviolet one, and I'm talking about that because the suit is observing in near ultraviolet to look at the sun, but also to give input on this particular fact. So from 200 to 400 nanometer, it comes all the way within the ozone layer, and that is where you have the oxygen and ozone. And these photons, then they work as a catalyst to break oxygen and break ozone and so on and so forth. So the whole chemistry gets defined depending on how much is the solar radius. I'll skip this. So to keep these things in mind, this is just the state of art, how much we know this radiation within that particular waveband from 200 to 400. This is the wavelength, and this is what is plotted from sun as a star spectrum, right? So you can design an instrument. I don't want to look at the spatial features, but I will consider sun as a point source and keep observing the spectrum in different lines. And you can do that. So there are different instruments. Here, the left axis is for 242 and below, and the right axis is 242 and beyond, and that is essentially because the solar rate flux changes by a few orders of magnitude. So the plot would be really elongated, and so that was a clever thing to do. There are models and data. Lean model is like whatever we know about the solar proxies and solar features, and we can work out how much energy is being radiated in that particular regime, and then compare that with what the measurements are showing, and what you can find is that there is about 4 to 6 difference below 400 nanometer. Beyond, it is lower, and below, it is higher, right? So there is a huge discrepancy between what we can measure and what we have modeled based on that. So we aim to produce that input which can help understand this relationship better. So keeping these things in mind, we proposed this instrument. A number of institutes involved. We call it Solar Ultraviolet Imaging Telescope. This is one of the instruments on board Aditya L1 mission of ISRO, which was launched in 2023. I'll just give you a little bit timeline. I find it interesting to tell you that how long it takes to make these things. So if you get into a project which is taking a little longer than you anticipated, it always happens. So the announcement opportunity came in 2013. And with the deadline, 13. So we had 16 to 18 days to prepare a proposal to send it to ISRO. I think there were 28 proposals sent. Out of that, 7 were shortlisted. We projected this solar ultraviolet imaging telescope to look into ultraviolet wavelength. So there are 4 instruments which are doing remote sensing, essentially looking at the photons, covering all the way from visible to hard X-ray. And that is because I showed you that, to map the whole range, you need to have those whole frequency. And then you have all these particle instruments looking at the solar wind mapping, all this plasma which is coming along those field lines as I show, open fields. And also to measure magnetic field at the L1 point, just to see how the magnetic field of the sun's ejecta is oriented, to see if it is going to reconnect with the Earth's magnetic field or not, because the direction of the magnetic field plays an important role if a solar ejecta is going to be geo-effective or not. So we went through all this, and then the final approval we had in 2015. So about 2.5 years. And then it took us 1 year almost to sign an MOU with ISRO so that we start receiving the funds, okay? And we launched in 2023. So exactly almost in 10 years from the date of submitting the proposal and launching, 10 years it took. Okay, now what is SUIT? So SUIT is essentially a medium and narrowband filter imager. It's a telescope. It has different filters, and it images the sun in the wavelength band of 200 to 400 nanometer. And of course, if you want to design an instrument, you put all these constraints. It has to be lowest trilight, very, very high contrast we want to measure, and so on. Because unless you define that, then the engineers will not be able to then change it into a spec or engineering a spec and so on. So you have to put all these numbers and so on and so forth. We also wanted to look at the missing region in the solar atmosphere, not only the one which has already been done from outside and west, to find a niche region which can complement as well as give new information. So we wanted to go for the lower and middle atmosphere. It's giving you 2 things, one arrow killing 2 birds, essentially to look at the coupling and dynamics of the atmosphere, plus also the spatially resolved, not sun as a star measurement of irradiance, but also look at different features in near ultraviolet to try to understand how it might affect the Earth and the ozone layer. And as I said, we want to find a niche area. It was done, technology demonstrated on these balloon-borne experiments and some very old, in 70s, spectrograph where very limited data were taken. So the science goals is look at the dynamics of the atmosphere and essentially look at the flares and so on. Climate studies, because we will be the first one to provide the spatially resolved, that you take the image in the region where the irradiance or the energy coming out from the sun matters the most for the ozone layer and ozone and oxygen chemistry. And of course, regular studies where how the eruptions happen, how the atmosphere is heated, and so on. So I'm sure a lot of you are experimentalists. You would like to see what the design would look like. So this is the CAD drawing. So this is a small telescope, 14 centimeter as a primary aperture. The sun is shining from that side. coming in, they have a primary mirror, and then you fold it to go through a secondary mirror, and then you also have a shutter to control the exposure. It's a vane shutter, so there are 2 holes in that. So you rotate it and modulate the rotation in such a way that it exposes a given pixel for the time you are trying to make that exposure. Okay, and then we are observing 200 to 400 nanometers. We want to slice through the atmosphere by using multiple filters within that, right? So we have used 11 filters. So instead of giving those 2 data points, now we give 11 data points within that 2,000 kilometer range in the atmosphere. And then you have 7 extra for the upper atmosphere. So you have a seamless coverage of what is happening on the surface all the way into the atmosphere. And then the light goes through the filters, and the filter just tunes into the waveband you want to, and then there is a detector which takes an image at the end. Now, one of the problem is that entrance aperture filter that we call door assembly, there is a filter there because sun is radiating in all the waveband, and most of the radiation is in visible light and so on. So if you let the whole visible light come into your telescope, it will heat up, right? All the waveforms will get deformed. You'll not be able to do good imaging and so on. So we had to develop a new, and since nobody had looked into these wavelengths in altogether, and the flux changed by 2 orders of magnitude in these wavelengths, we had to design, and there was a company in Mumbai with whom we could do this. So the design was done from us, they do the testing and so on, and then it has to be space qualified and so on. So we are very proud that we developed that technology, and it was done not off the shelf. We developed it and put it up there. It was done by a student who was of Arthana Ghosh. Now she is working in Tata Space Lab, right? So being in academia doesn't stop you from going to industry. Okay. Now, if you cover it all up, this is how it looks like. Huh? It's a beautiful thing. You spend 10 years, and this is what it exactly is flying. This is the flight model, and all these multi-layer insulator coating has been put in. And some people say, oh, there is so much of gold. It's not gold, it's just plated like that. And the light, again, now the aperture, the entrance aperture is from this side. So it's like about 1 meter, some 60 centimeter width, and then some 50 centimeter in height. It is going to observe this particular range of the wavelength from 200 to 400 nanometer, essentially to cover this part of the solar atmosphere. And that part, essentially, as I said, that graph is a little misleading. It doesn't bring out the whole thing, but if you just put it in log, it just appears better. It goes from the bottom left, that inset. The bottom left is 200 to 400, and the change is about 2 orders of magnitude over there. And this is where all filters are defined. And these are the spec that we also want to observe the continuum, we want to observe the emission lines, and so on and so forth. This I think I showed, and that's the cover we have. So in this, where we have 3 data points, we have additional 11 data points in that range. We observe in different modes. It's a completely programmable telescope. Every day, the command is sent. The way you want to observe it, you write a proposal, you choose which filters you want to observe, because which filter you want to choose depends on your science goal, right? Maybe you want to do a very fast observation, so you choose 1 or 2 filters that you can take imaging in that. Therefore, you'll have cadence of observation better. If you want full thing, then of course you can do that. So this is all just saying. Now the other thing which I would like to highlight is that the flares I showed, that big eruptions, we don't know when they're happening. And they actually give you the most extreme physics, and that's what you're interested in trying to understand, because this is the first time we'll be observing in these wavelengths. And we didn't want to miss any opportunity not to observe them. So it would have been nice to keep observing the full sun all the time with the same cadence and so on. But it requires money. If you wanted to do that, then you would have needed to have 6 telescopes of that kind. So we can't do that. And also, even if you do that, then you have to store the data, and you are 1.5 million kilometers away at first Lagrange points. You have to transmit the data. So it's all not very easy. So what we did, based on all the prior knowledge we had by looking at other flares and so on, we have developed an algorithm which works on board, which takes the data in a parallel stream, keeps it processing, and depending on the parameters that we have set, and it's still flexible, we can still set it and change it and so on, it localizes the flare by itself, and whenever it sees that there is a flare going to happen or is going to happen or happening, it just gets into that particular region of interest and it starts observing it. So far, this is the first time that it has been implemented such things, and it's working. It has been implemented earlier also, but I think Hinode, but they were scared to switch it on because, anything you switch on new, it requires confidence and so on. So we did it, and I think at about 40% time we are being successful to observe those flares, so which is good news. Okay, if you are interested in these kind of details, of course, the telescope design is like that. The focal length is 3,500, and that is why we had to fold it to make it compact. The cadence, as I said, if you want to take full disk images all the time, then every 20 seconds you can do that. But if you want to read out a smaller region, then you can every 4 seconds you can have an image of the sun. And these are the mass power. So the total mass of the whole instrument is about 42 kilograms, and it takes 35 watts of power. These are just some observations. Now we delivered this payload in 2023, and it was launched on 2nd of September 2023. Can you hear something? So that is a rocket, and it's not a random rocket.
5 seconds.
It's
Magnificent liftoff of PSLV-C57 with Aditya L1 on board.
Yeah, so I stop it there because just to make sure that it's not a random rocket, It is the rocket which took Aditya L1 away. Okay. Fine, so after it was launched, we're left with these plumes, right? And then you have spent your life. I joined IUCAA in 2011, and this opportunity came in 2013. So, and since then, you devote full time on these things, and whatever you delivered is gone, right? So you don't know where things are going, and it was not only with me. So with me, my colleague, Professor Ram Prakash, he is an instrumentation person, so I and him together, so I provided all the science feedback. He converted into engineering and all that. So there are 2 PIs on our payload. And then there were 6 other payloads, so 6 other PIs. And if you can look at this picture that shows that thanks God it's gone after 10 years, but oh my God, what will happen now, right? So it's always that moment of this thing. And it's also not very fast that, next day you can switch on and you start getting the data. It takes about 110 days to get into the orbit, because it has to go around the Earth, maneuver it, get a critical velocity, then they inject it, and then it keeps going, and it takes some time. So everybody was nervous. Let's switch on the payload. What will happen? And the project will say, why are you not switching it on? But you are also scared, in flight, what will happen? You don't know the environment and so on and so forth. But eventually, we were pressurized, and also we were pressurizing ourselves to see what's going to happen if things are working. On 20th of November, before the satellite was injected into its final orbit, we switched on the payload, and we saw that the current was flowing. We got the signal that the instrument is working. And this is our project director, Niga Saji. Now she is retired. And that's the team of IUCAA and ISRO. That's the mission director at the back with the blue badge. So that was a happy moment. But still, we had not opened the door. So we didn't know if some picture is coming inside or we're getting any image and so on and so forth. But that happened still before getting into the final orbit, after we checked all the electronics components were working on December 6th. So ISRO has done a clever thing that it has installed a camera which looks at the door of the instrument. And the reason is that they didn't want to, okay, in a funny way, they didn't want anybody to blame them if the sun's picture was not coming in. Oh, the door is not opening. How would you know? You're given a command, pulse has come, the door is opening or not. So they installed a camera to see if the door is opening or not. And we wanted to have a multiple door and opening and closing because of the contamination purposes. So that's the suits door, and that's the door of another instrument, that's the coronagraph. So that was opened later on. So the door opened, and the first image we got of sun was that in our detector. So that was a very, very nice and happy moment to see that the sun has fell through the entrance aperture door and everything is aligned, and you're getting an image of the sun. And nice thing was also that this is just raw data. You just take the image and you scale it to min and max, the way you play with the photographs. And you can see all those features that you usually see on solar images, like those plus regions, those bright regions and dark sunspots and so on. And this is the chromospheric image, so you wouldn't see those coronal holes and so on and so forth. As I said, we had 11 filters, so we had to check each and every filter. And of course, in all of them, we got our sun nicely. You can notice all these artifacts still, because as I said, it's a raw data. So all these stripes you see, right? So those are flat fielding in the detectors and so on, dark currents not removed and so. And the sun was very active on that particular day. It also showed us this, that prominence thing, off-limb plasma just hanging and wobbling around. Now, the image is doing this. This is essentially because the sun, the spacecraft has not reached its orbit. It's traveling, so it's doing all kind of jitters, and that's what you're observing. You also see that in the bottom left, there is a flickering. That is because we have this shutter, right? So your two vanes are there. We figured that something during launch must have happened or something happened, that depending on which orientation you are, there is a difference in scatter light, right? And the difference is less than 2% or something, right? But that still comes out in your images like that. So now we can correct all that, but that was first image, so we just put it in. It also shows that, and the scatter is larger, as you can see, in the bottom left corner than everywhere else. We can also observe these small field of views. And as I said, you can go for faster readouts and so, and you can imagine all these sunspot regions and the scattered bright regions, which we call plas, and these are the strong field regions, which are, so this is one of the first active regions which are ever observed in these kind of wavelengths simultaneously. I also said you can do it faster, and you can look at the dynamics of those, and you can see all this flickering happening on this, right? It's a chromospheric image. This is again raw, and you can see all this in raw images. Once you process, you will see even much better thing. Those flickering, now we know that what is happening is those electrons, possibly which are precipitating from top, which are coming and hitting the chromosphere, and those plasma is just emitting and giving you those kind of flickers. And that happens, now we know, because of some magnetic field cancellation on the surface, which is essentially mimicking reconnection. You see this black, dark and this thing is just because of the shutter thing. It's just changing there. And that was this large scale eruption which produced a CME. So these two of the students are working on these two events. But we also have looked at flares, for example. This is one of the events that happened on 31st of December 2023. It's still before the spacecraft was in the final orbit. And what you observe here is a plasma blob, which is just going, erupting, and getting out into the heliosphere. You can see all these bright features. We know that there are post-flare loops, and this is the first time we observe so high in these kind of wavelengths because the dynamic range of the instrument is good. And when we combine all that with multi-wavelength observations, we see these non-thermal radio bursts, which are matching with the kinematic profiles of these plasma blobs which are going. So essentially telling you that these non-thermal bursts are due to reconnection and then pushing these plasma away. Now all the data is processed. Full disk data has been put in. Full disk data is available online for anybody to go and play with the data, do science or whatever. That's the kind of quality of data in the fully processed form that we have put in. Another flare that we observed, and I wanted to show this, this came out on our Science Day. So that happened on 22nd of February, and that flare happened in that region. And that was not by detection of the flare. We just were lucky that the region of interest were there, and we observed it. And what you see here is that the chromosphere, the lower atmosphere, responds exactly at the same time when you have this hard X-ray burst of hard X-ray burst is happening, and also mimics exactly the same time when you see this very strong rise in the temperature in soft X-ray. So you can imagine that how things are happening in higher up in the corona combines well with what happens because of the electrons moving faster at the photosphere in the chromosphere. So with that, I summarize. Here is another observation taken from SUIT. It's an unique instrument. I invite you all to look at the data, play with it, and do science with it if you like to do solar plasma physics. Thank you very much.
Thank you, Professor Tripathi, for a wonderful talk. And we all like to congratulate you and thank you for bringing these fantastic images and the fantastic science which was unexplored previously related to the solar physics. I think the entire team of Aditya L1 and SUIT deserve a huge applause.
Thank you.
Now, talk is open for the questions. The floor is open for questions.
So I have a very simple question. So you showed us spectrum of sun in various like UV, X-rays, and you chose some colors. For example, for X-ray you chose red, and for UV golden. Was there some motivation to choose these colors, or just aesthetic?
I mean, okay, I should have said, they're all false colors, right? Because ultraviolet color is not defined. So depending on the image you're looking at, sometimes choosing the color table makes you see things better and different in different color tables. So you play with the color table, whichever matches the best, then you use that because you want to highlight active regions differently than, for example, very dark regions. But if you're sometimes, so there are some standard color people just define mission-wise, okay? But sometimes you're looking at feature which is not coming out as well seen as you would like it to be, then you play with the color table, change the contrast. Sometimes you write your own color table to bring things in and out. So,
Yeah, thank you.
Okay, thank you for your nice and good overview of L1 mission. In the video slide, you have shown flares are rotating like structure. So what makes the flare rotating?
you mean
One of the video you have shown.
this one? This one?
No, not this one.
Trace.
Flare.
Yeah.
rotation.
This
Yes,
one.
yes. Third one, top.
Yeah. Okay. So these loops that you see, right? They are post-eruption loops, post-reconnection loops, right? Now imagine these cartoons are in 2D, right? Now imagine there is a 3D structure like that, right? And the system erupts, the reconnection can proceed either from this direction or from this direction or from the center. So depending on how the reconnection happens, which direction it moves, these loop dynamics will also happen accordingly. Like for example, in this case here, in the bottom left, right? These are nothing but the foot point of all those loops that you would see. So if I had an EUV image of this, and if I overlay, then these bright ribbons, they're exactly at the foot point of those magnetic loops. And that is the way the neutral polarity inversion line, if you like, is defined within that system. Yeah? So let's say if I have a system, I perturb it from this location, then the system will erupt like this. And we see this, loops are, the ribbons are propagating like this in one given direction, starting from one side, right? So that is where, how you start the eruption, and that essentially leads the way the reconnection proceeds. We also see not only this wave movement, but we also see the separation, right? So if in the neutral line, polarity inversion line, we see outer and outer field lines are getting into reconnection, you see this separation. And that is one of the ways to measure reconnection rate in solar physics. Because the way it will separate, that will mimic the way the field lines are pinching together here. So by looking at this, you can measure the reconnection rate because you also know the outflow.
Okay, thank you.
So normally the temperature of the solar corona is higher than the temperature in the solar atmosphere. So why is the extra energy it is coming from in the?
When you say solar atmosphere, that's not correct. It's higher than the solar photosphere. Because corona is also part of atmosphere. It's coming, that's what I thought I tried to demonstrate, that it's all coming from magnetic field. The question is how and where the magnetic field is getting that energy. And that I didn't touch upon. That is essentially because of the convection. Right? On the surface, you have this convection. And convection is doing what? You have the magnetic flux tubes, which are coming from inside out in the atmosphere. The convection is doing mechanical work on these field lines. That mechanical work is getting converted into magnetic energy, and the magnetic energy is just storing it. Now, because we know how much mechanical work is being done, we can work it out, and then we can work out that how much is the Poynting flux which is bringing the energy up. We find that there is enough energy in that mechanical work to actually come and hit the corona. But then the question remains then how actually you dissipate it. Okay? So the source is magnetic field and the mechanical work at the surface.
Thank you.
So, hello sir. I have a very nice question that you said that there is due to that visible photon that increases the energy and means that it hits the instrument. So you put some filter there. But the UV photon has a more energy than the visible photon. So how they can...
Yeah, but the UV flux is also very tiny.
Okay.
Right? You look at this. Look at this. This is plotted. So you're talking about 0.1 versus 10 to the power 4.
Okay. So that range that matters.
So very, very tiny flux. Even we don't allow that much of photons to go, that energy. We only allow 0.2% of the UV photons to get into the instrument.
Okay.
The rest all we have this filter which just rejects that light out completely.
Okay. So, thanks sir.
Thank you for a nice informative talk. I have a curiosity question. You said, if I heard correctly, that you said that the total radiated power is constant over the solar cycle. However, the 200 to 400 increases up to 60% in there. So, if the total power is constant, so then some power is getting lost or somewhere. So, just clarify that. Yeah.
No, okay. Let me get to this. So total power from solar minimum to solar maximum changes by 0.1%, right? That is why we call it solar constant, which is no more a constant, right? 1.3 something something. And that is what is shown there. Of course, there are large statistical error bars and cross calibrations and so on. So that is 0.1% change, right? Now, if you take the spectral energy distribution, that is the total energy, total all the way into the electromagnetic spectrum. Now, if you take the spectral one, so for example, here if you see, the red curve, now it is going in the log here, that is why you see this drop in the irradiance. Below 400 nanometer, right? The total contribution into the in the total energy is only about 8%, right?
So you don't see it in there.
You don't see it. So only 8%. But if you look at the changes, the change happened the largest in that regime. But when you look in the total, it's very tiny with respect to that. So anything just comes into the measurement errors and so on.
Thank you. And second, just another question is that what kind of detector you have used for measuring this?
This is a CCD.
CCD with X-ray CCD or something?
No, so it's a UV thinned CCD, which, let me just tell you this. It has specifications. So what we do is a space grade UV qualified. What they do is in the back they have this UV thinning. They do, and look at the normal CCD, charge coupled device, essentially.
Thank you.
The details, if you want, is here. Yeah, it's a back illuminated UV enhanced CCD.
So if no more questions, we'll thank Professor Tripathi again.
Thank you so much.
So next talk is by Vijay Dalal.
Good afternoon, first of all, and thank you for giving me this opportunity to talk about effect of less than 2 MeV. So to talk about the effect of less than 2 MeV ions associated with interplanetary coronal mass ejections, CMEs, but ICMEs, on the magnetospheric ion environment of Earth. So now, to start with, we have flare here, and Professor Tripathi has already elaborately discussed this flare aspect. But in most of the flare cases, there is this coronal mass ejections, which are actually eruption of huge mass and magnetic fields from the sun, and that can propagate through the interplanetary medium. And ahead of CME, there are these shock front, like interplanetary shocks. These shocks can accelerate energetic particles, and also from the flaring side also there are energetic particles that can travel along the magnetic field or interplanetary magnetic field. Also the CME shocks, the energetic particles produced from the CME shocks, these are also very high energetic particles, and we call them gradual solar energetic particles, or GSEPs. Now CME, they can affect or interact with the Earth's magnetic field, for example the magnetosphere, in two terms. One is the energetic particles that come generally well before the shock physically come at the L1 or at the Earth's orbit. And secondly, when the CME or the magnetic field of the CME that come at the Earth's location, then they interact with the Earth's magnetic field or the magnetosphere, and they can drive geomagnetic storms, substorms, etc. Now, therefore, within the Earth's magnetosphere, there are two different sources of energetic particles. First one is the inner source, which are like geomagnetic substorms that are generally driven by CMEs sometimes other structures, for example, like co-rotating interaction regions or etc. But I will not talk about that. So what happens when a CME interacts with the magnetosphere, the outermost magnetic fields of the Earth's magnetosphere, they are actually swept away in the night side of the Earth, and then at some point of time, at a particular at some distance in the night side, these magnetic fields, they actually recombine or reconnect. They actually reconnect, and because the magnetic field lines were stretched at this process, some magnetic energy was stored at that point. And when magnetic field reconnect, it tries to dipolarize again, and the extra magnetic energy that actually accelerate particles, and those particles, as shown here, they are actually injected into the Earth's geosynchronous orbits. And if any observer is there nearby, they will see enhancement in the electrons, energetic electrons and ions. And sometimes they see dispersion-less injections, so that means different energetic ions, they enhance at the same time, and sometimes they can show dispersed, they can see dispersed energetic ions. Now, one example I am showing here for a known, this feature actually is called geomagnetic substorm. So for a known geomagnetic substorm, we see these dispersed protons from the geosynchronous orbit, and the typical spectral index or the slope of this spectra is around 5 or more than 5 in case of substorm injected particles. And the outer source of particles that constitute like solar wind particles, then suprathermal particles, and also the gradual SCPs, impulsive SCPs or solar energetic particles, and also some amount of galactic cosmic rays, anomalous cosmic rays, etc. Although solar wind ions, they are less energetic to penetrate directly the Earth's magnetic field or magnetosphere. These suprathermal ions and very high energetic particles, they can directly penetrate with different conditions, and particularly greater than 10 MeV energetic ions, they can directly penetrate the Earth's magnetosphere and can like modulate the particle environment there. Suprathermal particles and solar energetic particles having greater fluence and energy, they can actually harm the some space-based technologies and resources. But the question is, how less than 2 MeV energetic particles or ions, they affect the magnetospheric environment? That we wanted to study. Now, Professor Tripathi also showed the launch of Aditya L1. So after the launch, Aditya L1 was actually rotating around the Earth several times. And on 19th September 2023, it was in a trans L1 phase. So during this earthbound phase, one of the in situ payload on board Aditya L1 called ASPEX STEPS. ASPEX stands for Aditya Solar Wind Particle Experiment, and STEPS is Suprathermal and Energetic Particle Spectrometer. So we didn't wait for like 110 days. Instead, after 7 days of launch only, 2 detector units of STEPS, which is Parker spiral and not pointed. STEPS consist of 6 detector units, but 2 detector units, NP and PS, they were actually turned on. And during this earthbound phase, we got data like less than 2 MeV ion flux from these STEPS to STEPS units. Since Aditya L1 was traversing through Earth's magnetosphere, magnetosheath, and also sometimes in the through the interplanetary medium, we have data from these 3 regions also. So these are the observations. So first 2 panels are the STEPS PS and NP detector fluxes at different energy channels. The third panel shows you the red one shows you the altitude of Aditya L1 with respect to the Bosock nose, like Earth's Bosock nose and magnetopause nose. The fourth one is the CMH, which indicates geomagnetic storms. Luckily, during these phases, 3 ICMEs actually hit Earth. These are shown here by this magenta color vertical lines. And as you can see, after the ICME 1 here and ICME 3, there were 2 geomagnetic storms, and the intensity of the storm were almost similar. And these are other interplanetary in situ measurements or solar wind measurements, like magnetic field, flow pressure, etc. Now, as you can see here, that the green colored intervals, they have specific meaning here. The first one, we can see the IMF BZ, like the north-south component of the IMF, interplanetary magnetic field, that was almost 0. And in case of the second green shaded line, in this one region, it was almost positive, and in the third one, it was negative. Now, why we wanted to show this, I'll come later. And also the other shaded regions here, yellow shaded regions when Aditya L1 was in the magnetosheath, gray when it was in the magnetosphere, and pink one when it was in the interplanetary medium. Now, generally, co-located magnetic field measurements should be there to identify these regions. But unfortunately, we didn't have that measurements, like magnetometer was not turned on. So we use model to identify or for the demarcation of these regions. And also Parker spiral and north pointed of detector units of aspect steps, that should be along the Parker spiral and the ecliptic north. But during this phase, the orientations were not like that. So I will show. So here are the different regions at the start and end of these intervals. And for modeling, we use these things, like the magnetopause distance is calculated from this, where we used real-time data of solar wind velocity and density, and these curves were drawn from these parametric equations. And as I said, North pointed was looking on along the Earth with some angle, and the PS unit that was almost above, that was looking at the sun above. So these were the orientations. Now, once we get those fluxes, we calculated the spectra of ions at these particular intervals, the shaded intervals. So this is a very busy plot, and you can probably can't understand anything about that. So what we will do, we'll tabulate the spectral indices, like the slope of those curves here for different regions, like when it was in the magnetosphere, when it was in the magnetosheath and IP medium. Now again, understanding something from this is difficult. So again, I will simplify that during interval 2 and 3, the spectral index observed by PS, NP and MPS, okay, I must say, sorry, I must say, along with these aspect steps, we used some measurements from the L1 point, which is coming from the Advanced Composition Explorer satellite, and also to assess the environment of the magnetosphere, we use this GOES 8, which is in the geosynchronous orbit measurements. So we compared all those spectral indices and summarize here that during interval 2 and 3, steps units and this GOES, which was inside the magnetosphere, that showed spectral index around 5. But LEMS, which is instrument at the L1 point, that showed around 1.5. In 4C, LEMS, PS and NP, they showed spectral index less than 3, and MPS 5. For 5C, we can see again it's 2.5, and like MPSH showed 3. So here you can see that MPSH, it showed less spectral index. In case these were during the magnetosphere, and in case of magnetosheath, what we can see in interval 1, PS, NP and LMS, they showed less than 2.5, MPS again 5, interval 4B, steps units and LEMS less than 3, MPS 5, and interval 5B, all showed less than 3 spectral index. Okay. So now, and also, sometimes we have seen there is anisotropy in the spectral indices as observed by PS and NP units. Now, and in case of 4 and 5B, we can see the spectral indices are around like 2.5, 2.3 and around 5, and also in case of very hard spectra. So what are the outcomes? Now, the condition is that energetic particles from the interplanetary medium, they have little bit hard spectra. That means the spectral index should be less. And as I showed earlier also, the particles that are generating within the magnetosphere, they have generally very soft spectra, and the spectral index is around 5. We have seen in most of the cases, the spectral index within the magnetosphere as observed by GOES was around 5. But in some cases, the spectral indices goes below 5 and is around 3. That shows that there is probably some contribution of the energetic particles from the interplanetary medium into the magnetospheric particle environment. And in case of magnetosheath, you can see that the spectral indices are always in the middle, like average 5 and 2.5, some average value. So there is a clear-cut mixing of energetic ions from the IP medium and magnetosphere in the magnetosheath region. And as I said, that there is some directional anisotropy because NP and PS unit, they observe particles coming from different directions. There is directional anisotropy as well. And this may be due to some closeness of the, to the bow shock, orientation of the ischemic shock, and some other effects of substorms, etc. Because we can't assess that aspect. And there is some possible dominance of substorm injected particles in interval 2 and 3 because steps units and GOES both showed spectral index around 5. This aspect is further verified by using this Gauss electron flux and also the magnetic indices, which shows like geomagnetic substorm indices there. If there is substorm, then there is, as you can see, this is a clear-cut signature of substorm. So we can say that before interval 2 and 3, there was substorm, and those particles were actually in the magnetosphere and aspect steps that observed those particles, and the spectral indices is therefore like kind of around 5. And as you can see that during interval 5, 5a, 5b, 5c, although there were different like regions like magnetosphere, solar wind, and also in the magnetosynth region, but still we can see comparatively harder spectra, like spectral index less than 3 for all the instruments. For example, aspect steps, the Gauss, and also the Gauss mainly. So what happened there? To investigate that, we actually directly compared the measurements from ACE and measurements from Gauss at different energy channels. And further, we calculated the shaded region here. Okay, the shaded region here at the time period just before the shock. Like there are 3 ICME shock, and before the shock, because those particles are coming before the shock. So before the shock, we identified these regions and calculated the correlation coefficients between the energetic ions observed at the L1 point and energetic ions that are observed from the magnetosphere. So we see for ICME 1, there is almost no correlation. For ICME 2, there is very mild, we cannot say this is a significant correlation. This is very mild correlation for high energy particles. And for ICME 3, we can see the correlation coefficient that increases along with energy. So that shows that before ICME 3, the energetic particles, they clearly entered into the magnetosphere and hardened the spectra. So we can see here. Now the summary. So I have showed you the first measurements from the aspect steps instruments during the earthbound phase of Aditya L1. Also, we have seen the important role of IMF BZ, because when BZ is negative, energetic particles enter the magnetosphere easily. We have seen evidence of injected ions in the magnetosphere in interval 2 and 3. There is mixture of energetic ions from both the magnetosphere and IP medium in the magnetosynth region, and also direct entry of less than 2 MeV ions from the interplanetary medium to the magnetosphere. So that is clearly visible here. And also the most important thing that the 2 ICME events, they induced, similar intensity geomagnetic storms, but the energetic particle wise, they showed different effect on the magnetosphere. Now these results are actually currently under review in ABJ, and this is the paper. With this, thank you for your attention.
Thank you, Vijay. So now floor is open for questions.
Yeah, I have a question.
Yeah.
So, did you, from your measurements, you said there's a direct entry of 2 MeV ions, right? So, do you also kind of track from your direction pointing in which direction these 2 MeV are going?
No, we didn't track those.
You didn't track. So,
No.
but how do you know then it is a direct entry in that sense?
Yeah, that is because that when there is entry of this harder spectra, hard spectra energetic ions from the interplanetary medium within the magnetosphere, the contribution is so that the particle spectra at the magnetosphere should be hard again. So we see generally magnetosphere occurs 5 spectral index, but in case of direct entry, we see the spectral indices actually directly comes down. That's our.
Okay, but you also have something on sun pointing, no?
But that was not on the sun pointing all the time, because it was showing, seeing the sun like this, like there is an angle. So we don't know from where it is coming. Yeah.
Okay. Thanks.
Yeah. Thank you, sir.
Thank you, Bhargav. So if there are no more questions, thank you, Vijay, again for a very good talk. So next talk is by Johan Sharma.
So, very good afternoon to all. My name is Johan Sharma. I'm a PhD student at IIT Hyderabad under the supervision of Dr. Keith Kumar Makwana. So, the topic of my talk is current sheet at electron scale in kinetic wave turbulence. So these are content of my talk. So first I will give a little introduction about solar wind and magnetic sheet. Then I will go to turbulence and intermittency. Then I will talk about some of the satellite observation. Then I will go to simulation setup, and then 2D, some of our 2D and 3D analysis. So first of all, solar wind and magnetic sheet. So what is solar wind? So solar wind is basically a stream of charged particle that is continuously coming out of the sun. Mostly it consists of electron, proton, and some of the heavy ion like carbon, nitrogen, oxygen, etc. And magnetic sheet is the region, and magnetic sheet is the region between the bow shock and the magnetopause. The bow shock is the region where the fast solar wind coming out of the sun is first interacts with the Earth's magnetic field. And magnetopause is the region between the Earth magnetosphere and magnetosheath. So you can see in this depiction here, the blue region is the magnetosphere, and this orange region here is magnetosheath. Now, there are some general model approaches to understand space plasma like magnetosheath and solar wind. These models are MHD model, kinetic model, and hybrid models. So MHD models are basically large-scale models that describes the overall structure of the solar wind plasma or the magnetosheath plasma. In MIT models, it is considered, the plasma is considered to be made of a fluid, and the MIT question for this fluid is solved. Then there are kinetic models, which describes the small-scale interaction in the plasma. So they discuss the physical processes that results in heating and acceleration of the solar wind and magnetosheath plasma. For them, another set of equation called the Vlasov-Maxwell equation is solved. Then there are hybrid models, which are kind of hybrid between MHD and kinetic models. So they consider plasma ions and protons kinetically as particles, and electron as neutralizing background fluid. Now I will discuss a little bit about turbulence. Now turbulence is a broad topic, but I will give a little introduction. Now if we follow Tissotowicz definition, then any system with these three properties can be called turbulent. If it is, it should be random and irreversible. There is a excitation of fluctuation over a broad range of scale from very small to very large scales. And there is an exchange of energy between these fluctuations. On the right here is one of the sketch by Leonardo da Vinci, where he's trying to depict the flow of water from a channel into a water body. So you can see the channel is continuously inputting energy into the water body, and small and large scale vortices are being formed. And there is an exchange of energy between these vortices. So this system is turbulent. Now cascade is one of the important property of the turbulence. Cascade is a process in which it tells us about when some quantity transfer from one scale to another, for example, energy. Now, I will talk a little bit about intermittency and kurtosis. Now, intermittency is one of the fundamental features of the turbulence. So, intermittency is associated with observed brustiness in the turbulence. So, it indicates strong and localized fluctuation. For example, the current sheet is one of the example of that. Now, kurtosis generally represents the tail or the peakedness in the relative to the Gaussian distribution. For Gaussian distribution, the kurtosis value is generally 3. Any value greater than 3 is generally considered a tail or peakedness in the Gaussian distribution. For a magnetic fluctuation, the expression for kurtosis is given like this, where delta B is the difference in the magnetic field between 2 points in space. A high value of kurtosis represents a strong intermittency in the turbulence. Now I talked about turbulence, intermittency, and kurtosis. Now I will go to some of the magnetic sheath and solar wind observation of current sheet and kurtosis. Cheever and all studied the high resolution data from MMS spacecraft in the magnetic sheet and in solar wind. They found intermittent structure in both solar wind and magnetic sheath. On the left is a kurtosis, scale-dependent kurtosis from magnetic sheath, and on the right is from solar wind. We can see in both the cases, at very large scale, the kurtosis value is close to 3. But as the scale decreases, the kurtosis value starts to increase up to 10 dI. The kurtosis value increases, but after 10 dI, it decreases in the case of solar wind. At proton scale, it becomes close to the Gaussian value. But in the case of magnetic sheath, it continues to increase up to the electron scale. So we can see that strong intermittencies are found in the magnetic sheath, but very weak intermittencies are found in the solar wind in these observations. Shruti and all also studied the solar wind through the MS spacecraft, and they found sub-ion and electron scale current sheet in their observation. Now I will discuss about simulation setup, but before that, I will discuss alpha and kinetic alpha wave because they will be useful for further discussion. So alpha wave, if you have a thread and you stretch the thread and you give some perturbation in the perpendicular direction to the thread, then there are waves set up in the thread. Similarly, if you have magnetic string and you give some velocity and magnetic perturbation in the perpendicular direction, then there are waves set up in the magnetic string that travel along the direction of the magnetic field. Those are called alpha waves. Now at very small scale, these waves are modified by ion inertia into what is called as kinetic alpha wave. Now in our simulation, what we have done is we have tried to set up the kinetic alpha wave. So for that, we have used the two fluid KW eigenvector relation from Hollweg and used them as initial condition in kinetic PSC simulation. Further detail of this simulation setup can be found in this paper here, right here, the second reference. So we have set up 3 such simulations with the 3 different mass ratios by keeping the same ion and electron temperature and same plasma beta. So these 3 simulations are with mass ratio 25, 50, and 100. So when we analyze the simulation at later times, we obtain high density current sheet structure in all these simulations. This is one of the screenshot from one of the simulation with mass ratio 50 at 600 omega pi inverse. So we see that high density current density structures are being formed. Now, to identify these current density structure, we have used 2 algorithms. One is the DB scan and another is the VFS algorithm. So I will discuss both of them. So DB scan is density-based spatial clustering of application with noise. So in DB scan, so first all the points above a particular threshold of current densities are identified. And after that, a certain EPS value is given to identify the neighbors, and a certain minimum sample value is given to identify the dense regions. After that, we take a point in the domain and search in the EPS radius of the point. If the number of points in the EPS radius are greater than minimum sample, then that point is identified as core point. And from that core point, all the points in the EPS radius are added to the cluster. If there is another core point in this EPS radius, then its EPS radius is also added to the cluster, and this process recursively continues to form bigger clusters. So this is one of the method. Then the other method we have used is BFS called the breadth first search. So in this method, first we form a cube of size n cross n and find the local maxima. So from that local maxima is 6 directions are searched: x minus x, y minus y, z minus z. So it is searched until it falls below a particular value f times gmx, some threshold value. And all the points in this region are added to the cluster. So that is other method, the BFS cluster. So after identifying the current sheet using these 2 methods, we find their length, breadth, and thickness using the PCA method, principal component axis. So in this method, so first PCA finds the 3 principal axes of the cluster. And it traces the 3 axes until the value falls below a particular threshold value. And the axis with the largest variance is identified as length, and the axis with the medium variance is identified as width, and the axis with the smallest variance is identified as thickness. So we identify the current sheets with BFS and DB scan algorithm and analyze them with PCA method. Now these are results from our simulation. So this is just the 2D analysis to see visual comparison between DB scan and BFS algorithm. So on the left is the current density Jz in xy plane from simulation with mass ratio 50 at 600 omega p inverse. The middle one is the current sheet identified with the BFS algorithm, and on the right are current sheet identified with DB scan. We see that almost similar current sheet are identified with both the algorithms. If you see each current sheet, the same current sheet identified in both the. But in some places, for example, if you see this point, if you see this current sheet right here, it is identified here but not here. Similarly, there is another current sheet right here which is identified in DB scan but not in BFS. So most cases they identify the similar current sheet, but in some places they complement each other. Next, these are the 2D analysis of the current sheet with 3 simulations to visually see how they are changing. So this is the current sheet from simulation with mass ratio 25, 50, and 100. We see that the thickness of the current sheet decreases with increasing mass ratio. If you look at this structure right here, it is thick. And if you see this here, it becomes thinner, and here it becomes more thinner. So we see that the thickness of current sheet are decreasing with increasing the mass ratio. And also we have used the same parameters for analysis in all the three cases. And these are results from BFS algorithm, but DB scan gives the similar results. Now let us look at the 3D analysis of the thickness, length, and breadth comparison of these three simulations. So the analysis time for the simulation are chosen such that there is sufficient turbulence in the system and the current sheet are not distorted. This is done by looking at the delta BRS by B naught value. We have chosen the time from 600 to 1400 omega pi inverse. So in the bottom here are the simulation results of histogram of half thickness with mass ratio 25, 50, and 100 averaged over a time from 600 to 1400 omega pi inverse. On the top are written the average of these histograms. So we see that with increasing mass ratio, the thickness of the current sheet are decreasing. If you take the ratio of the half thickness from simulation with mass ratio 25 to mass ratio 50, it comes out to be √2. And similarly, if you take the ratio of thickness from ratio 50 to 100, it also comes out to be √2. So we see that there is a scaling of the current sheet thickness scales inversely as the square root of the order of square root of mass ratio. Now we also looked at width and length, but the width also decreases with increasing mass ratio, but there is no change in the length. So the length is not affected by increasing mass ratio. Now, if we look at the skin depth, ion skin depth in the mass ratio 25 case, here it is 0.2 di, here it is 0.14 di, here it is 0.1 di. So we see that electron scale current sheet structures are being formed in our simulation. Next, we also looked at the scale dependent kurtosis. Now, if you remember, I talked about that if you have a kurtosis value of 3, it represents a Gaussian. So we see at large scale, the value of kurtosis is 3. But as the scale decreases, the kurtosis value increases. And it increases up to the electron scale. So intermediate structure are being formed in all these three simulations at small scales. Also, the intermediacy of the simulation with mass ratio 100 is more than intermediacy in mass ratio 50, which in turn is more than in mass ratio 25. If you remember the observation from magnetosheath, you will see that the graph of our simulation is very similar to that graph. So these results are matching with magnetosheath observation. Now I will move to the conclusion. So the current sheet structure are being formed in our simulation that I initialized with kinetic alpha wave. DV scan and BFS algorithm give similar results for the length, breadth, and thickness of the current sheets. The thickness of the current sheet are decreasing with increasing mass ratio, which indicates the electron scale current sheet structure are being formed. And scale dependent kurtosis indicates intermediacy at small scales, and it also matches with the solar wind observation. Thank you.
Thank you, John, for a very good talk. So now, yeah, questions.
Johan, nice talk. I want to understand the square root 2 which you get, I mean to say, for the thickness.
Yeah, it is like...
Yeah, so now my question to you, is it because of the fact that you are using kinetic alpha waves for a peak simulations? Do you expect the similar scaling if you do an alphanic turbulence in MHD, let's say?
We have not tried that, but I'm not sure if it is due to...
What is the physics behind the square root of 2?
What we are seeing is like, because as we are increasing the mass ratio, we are pushing the electron scale to the smaller scales. So, and the mass ratio also we are increasing by a factor of like twice we are increasing. So generally the skin depth is inversely proportional to the mass of the like ion or electron. So by that we think it is because of that, because it is inversely proportional to the mass.
Okay. But it would be nice to check if it's true also with alphanic turbulence in MHD.
Yeah, we can try that.
Yeah. Okay, thanks.
Hi. So I have a question. How you created turbulence in your system?
So,
like, what are the conditions for your case?
So in our case, we are putting some waves. We are using kinetic superposition of many kinetic inflow wave as an initial condition. Then we don't know if they are producing turbulence. But we in our previous paper, we have looked at their energy spectrum and all. So in that spectrum, we are seeing some of the cascading behavior. Because we see kinetic wave at later times also. We see the cascading behavior, so we see the turbulence is there in the previous paper. So in this simulation, we are trying to see if current sheets are there.
So you plotted the energy spectrum, and
Sorry?
then you plotted the energy spectrum.
Yeah, energy spectrum.
And then have you looked into the structure function also? Like
Yeah, structure function we are looking at, like kurtosis is one of the fourth order structure function. We are also looking at the higher order structure function.
Like
there
you
also
can
we are
look
getting
into, sixth order structure.
Yeah, sixth order.
function.
We are looking at those. We are getting some results. Like I have not put them here, but yeah, we are getting sixth order
So
structure function.
what is the order of the scales of your intermittency structures?
A scale, like it is well, electron and proton scale, like as I showed you in the kurtosis is indicating it is proton electron scale, because you see higher value of intermittency at small scales. If you can see like this scale, this is electron scale actually. This is our ion scale or proton scale. So we see like intermittency is there.
Okay, fine. Thank you.
Any further questions? I have one question.
Yes.
So on slide 12,
12.
the previous one, yeah, here, so you have distributions.
Yes,
These are
yes.
sizes, right?
Yeah, these are histogram. Yeah.
Yeah. So why they are not Gaussians? Why
They are-
the distribution looks like more like a log normal than a Gaussian? Is there any physical process or reason behind it?
Like I don't know, but like we just
See, if,
like
there,
this
if,
is
if there are multiplicative processes, it means there are more number of random processes
Yes.
which are responsible for your
Yes,
the
yes.
size or the distribution which you are plotting. So, is there a more number of process than one? Which is
there
responsible?
could be more processes, but right now we are looking at just these processes, and one reason maybe it is not Gaussian is because like it is kurtosis also we saw that it is kurtosis value is very high at, in these cases. So maybe that is one of the cases it is not Gaussian.
So, if no more questions, we can thank John for a wonderful talk. So now next talk is by Aditya Sharma from IIT Indore.
Good afternoon, everyone. My name is Aditya Sharma, and I'm a PhD student at IIT Indore, working under the supervision of Dr. Bhargav Vaidya. First of all, I would like to thank you, the committee member, for giving me this opportunity to present my work here. And today, I'm going to talk about, present the simulation perspective to probing the AG and jet feedback across the cosmic time. But before going, I talk about the AG and jet feedback and all the thing. First, I would like to discuss about what the plasma, because this is the medium, that fundamental medium that we are dealing with. Okay. So plasma is often known as the fourth state of matter, and it is hot and ionized gas where the electrons are separated from the atom, and this make it highly conducting and extremely responsive to the electric and magnetic field that are present in that environment. And plasma is present everywhere in the universe, from the sun's corona to Earth's magnetosphere to jet from the AG and jets and the lightning on the Earth, and the experiment that we done in our lab for the plasma. So what makes plasma especially interesting in the astrophysical scenario, that it is not only governed by the gravity and the pressure that is present there, but also the magnetohydrodynamics process that work even in the extremely relativistic environment or the GR environment, where the frame dragging also moves the plasma. So now so these are the extremely high energy environment. So now we deal with such of the high energy environment, which is AGN, and AGN are the extremely luminous region at the center of galaxy, and they powered by the
accretion of matter into the supermassive black hole, and they can emit radiation from the entire electromagnetic spectrum. As the spiral matter goes goes toward the supermassive black hole through accretion disk, they emit the powerful energy either in form of radiation or the powerful relativistic jets. These jets are perpendicular to the accretion disk, and when these jets are pointed toward us, these are known as blazar, and there are some significant feature that we seen in this blazar that is known as, if we see the spectral energy distribution, we see a double hump. And the science behind this double hump, that the first hump is come from the synchrotron process, when the electron is spiraled in the magnetic field region and emit radiation. And this radiation, the emission of this radiation depend upon the electron energy and the field strength that is present there. And the second hump, that is correspond to the inverse Compton scattering of the photon field that is present in that environment. Either it is due to the torus that is there, present the accretion disk, and other photon field that is present in the environment. And sometimes majorly, the synchrotron emits the radiation and also get its radiation is scattered with the electron that is present in that environment, and that is known as synchrotron self-Compton. So if we go deep into this and understand the science behind it, so I here present a loss function that is present, and if we see the loss function, they are structurally similar, but the things that different here is the UB in the synchrotron, that is the magnetic field energy density, and in the inverse Compton is the UISO. If the field is isotropic, then the UISO is define the isotropic photon field that is present in that environment. And if the photon field is CMB, means cosmic microwave background, it is an isotropic photon field, the energy density also depend upon the redshift. If for the high redshift, we see the very initial stage of the universe, where the universe is just forming, and the lots of CMB energy density that interact with this jet and give the inverse Compton scattering. So that the thing that the high energy that comes from this process, there is a thing that clashes that either synchrotron is the mechanism that gives the high energy photon, or either the ICCMB process. So to understand this problem, we try to simulate a jet, simulate the jet in our system, and to make this simple, we just take a simple jet and try to see this evolution in different redshift. So to simulate the jet, we use the setup that is prescribed in the Bodo et al. In 2019, and the relativistic RMHD equation, relativistic minor hydrodynamic equation that we solve using the Pluto code. And the thing here, the plasma that is used is the relativistic, the jet we are taking is the relativistic, fully rotating and magnetized, and the plasma we take is the cooled plasma, where the thermal pressure is less than the magnetic pressure. And we inject the jet from the, if we consider the 3D domain, at the center of the bottom of the system, we inject the jet from the cylindrical nozzle, and these are the, we take the ambient medium as a constant, where the magnetic field is constant and the density is constant, and our jet is underdense, where the density is 10 to the power 1000 times less than the density of the medium. So if we do this, and the radial profile that we take with in the cylindrical nozzle, we see this a very beautiful jet, and this comprises all the physical properties, such as the spine of the jet, where the speed or density is higher, and the shock that we get, and the bow shock that we get when the jet is interacting with the environment, and the Kelvin-Helmholtz instability that arises due to the density variation, and all these things are there. Now, to get the non-thermal emission from the jet, we use an interesting approach, where we just put the non-thermal particle, known as the Lagrangian particle. When the jet is ejected, just we put a single particles at the initial stage, and these particles evolve. And these particles is the ensemble of the relativistic electron with a finite energy distribution, and the energy distribution we take is the power law distribution, whose spectral index is -p. And the evolution of this particle and how this energy changes depend upon the Fokker-Planck equation that also depends upon the local fluid parameter that is present there. And this equation contains both the adiabatic loss term and the radiative loss term. And here E dot is the radiative loss term, where we put all the inverse Compton, the synchrotron loss function. And chi p is the ratio of the Lagrangian particle number density to the fluid particle density. So now, with this evolution, if we see this evolution and evolve the n gamma, with the help of that n gamma, we plot the SED with the help of this, that is the new F new, which we use the Derman and Menon 2019 result. And this new F new show the total flux that we are getting in our system, in our telescope and all the thing. So here is the test particle that we put in our simulation and see how this test particle evolve with time. So where we just put a single test particle and we assign a particular ID to every particle, and if the jet evolves, this particle also moves with the fluid. And with this, the n gamma changes. So here is the energy. Gamma min is the minimum energy of the particle that is there, and the gamma max 10 to the power 8. And with evolve, the particle cools and the maximum energy goes down to 10 to the power 5 sometimes. And sometimes it will increase because this is a test particle. Sometimes the particle goes in the shock and the particle energy may be increased. So these are the things. With the help of, now every particle has the n gamma, and with the help of this n gamma, we plot the SED. And for now, we plot the SED for the two different redshifts to see either since the synchrotron emission is there for the explaining the X-ray emission or the inverse Compton. So at redshift 0.1, that is very near to our in the time scale. So we said that every time in the gray region shows the X-ray band. At every point of time, we see that the synchrotron emission dominates. And if we see at the higher redshift, initially the synchrotron emission dominates the X-ray emission, but as the time increases, the magnetic energy goes down, and the CMB photon energy that become more than the magnetic field energy density, and the inverse Compton scattering start to dominate. And the interesting thing is that the model that is proposed by the Wu et al. And the Zhu et al., they said that the fractional ICCMB model, but they don't have any simulation verification, or that they have some idea, they propose this model. So we try to simulate this thing and see can we see this in our simulation. So when we run this simulation and we see that after some time, before if the jet evolve, after some time the CMB photon density increases, dominate over the magnetic field energy density. So now to explain this thing, because the synchrotron emission depends upon the electron energy, so we plot that if the Lagrangian particle that has some energy distribution from gamma min to gamma max, we just plot the histogram and the probability distribution where we just choose the highest energy and plot it. So we can see every Lagrangian particle has some higher energy density, and we make a bin and we plot the histogram. We see that at the initial redshift, redshift 0.1, we see that there is lots of high energy particle are there. But if we increase the redshift, if we go back in time, the CMB energy density increases and cools the particle, we see there is significant energy loss, and this significant loss in the number of high energy electron that gives the X-ray via the synchrotron process. So we can say that this explains that the number of high energy electron if decreased, then how we get the X-ray emission from the synchrotron process. So now if we use this information and try to see that the sites where we get the radio emission and the inverse Compton emission, because in the whole jet, there is a very less number of sites where we get the high energy electron, and in the whole jet, because the electrons are there in the environment and the Lagrangian particle cools down, so we know that the thing that we can generally say that in the jet environment, the lower energy electron are there than the high energy electron. And to see the image, we can plot the X-ray and radio intensity. And if we see the radio intensity, because the lower energy electron there, so we get the emission from the whole jet. And similarly, the inverse Compton scattering gives the X-ray emission with the help of low energy electron. To get the X-ray emission with the synchrotron process, we have to have the high energy electron, and this only exists in the spine region because we inject the electron from the nozzle that lies at the center of the jet, and we have the collimated shaft that increases the energy. So these are the region where we can get the synchrotron emission, X-ray with the help of synchrotron emission. Now there's the thing that we can see that the radio, and not till now I have discussed that the high energy emission, which is the process that dominates in the either synchrotron or the IC, that dominate the X-ray emission. But due to increase in the CMB photon density and the electrons is cooled down, the So the radio emission is also affected with the help with this cooling effect. And to check this, we for the same jet, and because we didn't change the physical parameter, we take the other jet at the lower height. It's just at the time of 163 kilo here. It's not visible at and sometime another jet is at 881 kilo here, which is at around the 12 kpc. So now we can see, we can compare how the radio emission ACD changes with the jet evolve. So we can see that at the initial stage, this pitch band is show the megahertz and megahertz to gigahertz range, and at the lower region, in this region at the lower state, we doesn't get any peak. But if we go look at the ACD at the after 12 kpc or above 10 kpc, we see that there's a peak comes in a radio band 2. That's the also thing that we want to show, because this is the thing that is said by in the COLLOQUIUM 2017 paper, where they say that we get a peak in the radio band also, but they don't have any simulation or that 100%. They can say this with the 100% surety. They just get some sources with the thing. They don't have the particular, or maybe say that they want some kind of verification in that thing. So they don't have 100% clarity about this thing. So we try to simulate that. Either we can get or not at higher redshift. So we try to simulate this thing, and we get that there's a thing, if the magnetic energy less than the CMB photon density, and if for this particular jet, we can say we will get a radio peak in this megahertz peak in that region. And if we do any simulation, and if we doesn't check that our simulation is correct, we have to check with the observation either our simulation is correct or not. So we try to compare our result with the observation, where we see these are the black dots and the teal and the orange dot with some other with several data set, and we try to see that our luminosity that we get with our simulation is predict the high redshift trend or not. So we check this thing, and we plot the X-ray luminosity at 2 keV, and we say that if we jet at the higher length scale, we can see that we can say that we can follow the trend that at the higher redshift the luminosity increases, and the ICCMB is the process that dominates the X-ray emission. And for the radio thing, we can say that the synchrotron process is there, and we get the decreasing trend. Maybe at the redshift 0.1, it is not matching, because maybe there's some other jet that are there, and the parameter that we have chosen not that perfectly well, and the other process are there, the ambient density, medium, and the thing that are maybe the cases. But for this thing, we check this, and we get a perfectly well trend. So with this, I'll summarize my work. So here is the summary of my work. We can say that the synchrotron-based X-ray emission arise when the high energy particles are there. They may be arise due to the shock, and ICCMB-induced X-ray emission become dominant with increasing redshift and the jet scale. And ICCMB interaction also affect the radio emission by cooling electron in the cocoon region, causing the megahertz peak to shift in the high redshift. So with this, I'm thank you.
Thank you, Aditya. So questions? So if you go to your distribution, where you are showing the distribution of high energetic particles. Yes.
Okay. So
the next one.
Yeah, next one.
Yes. So you said there is a drop in the high energy particles as you go in high redshift. Are you confident about this statement? It's like, okay, this distribution could be like, if I change the binning, probably the significance may change.
So
how
but
confident?
We can get that the number of particles that are initially in that range. If you see that,
but that could be just a fluctuation, right? That could be just a fluctuation of your entire simulation, right? That is possible.
Fluctuation, I don't understand. Could you please elaborate?
Let's say if you run the same simulation 100 times, will you get the same value of a high energy particle? No.
Not the exact value is not something different.
That will be changed. Right? They will follow a certain distribution, right? With some width.
Yeah.
So now considering that width and your binning, there may be a possibility that there is a less number of particles may fall in certain bins, right? So this could be one of the binning effect as well. That's what I'm trying to understand.
Yeah, but the thing that I want to compare that for the two different redshift and you run the same simulation, you will see if there is a number of electron in this 10 to the power 8 to 10 to the power 10 region, at lower redshift, the number of particles in this range must be greater than the brain.
So yeah, if I see the last bin, they are not significantly different.
Because the number, how the particle increase, but yeah, not significantly, but it is less. The total number of particles is there. So this energy, if we increase the energy, so for the higher energy, it may emit in the gamma ray.
Yes.
Because that's the other thing is there. For me, currently I'm seeing the region of the X-ray band there.
So if there are no more questions, let's thank Aditya.
Thank you.
So next talk is by Pratik Patel.
So very good afternoon, all of you. So first of all, I am thankful to organizer of the conference, organizer of the conference for providing the opportunity to present my work today. So myself, Pratik Patel, and I am presenting my research work on the Prandtl number dependence three-dimensional Hall MHD turbulence. So in this presentation, first I will provide an introduction that covers a brief overview of turbulence and the solar wind turbulence. So in the second section, I will describe the governing Hall MHD equation and the method and direct numerical simulation methods to solve this equation. So next, I will present the results from our simulation. So first, I will describe so in this presentation, first I will provide an introduction that covers a brief overview of turbulence and the solar wind turbulence. In the second section, I will describe the Hall MHD equation and the direct numerical simulation approach to solve this equation. And then I will describe the result from our simulation that includes the energy spectra, which is obtained from our simulation. And then I will present the results on intermittency, which refers to the sharp and large fluctuation which are happening at the small scales. And finally, I will describe the structure function, which provide an insight into the multifractal behavior of the field. And finally, I will summarize my talk with the key observations from our simulation. So study of turbulence has a very long and rich history, particularly in the field of hydrodynamics. So in the turbulent environments are mostly characterized by the strong linearities which is present in the system. So your image on the left-hand side shows the turbulent flow which is generated by the placing obstacle in the laminar fluid flow. And after the obstacle, the with different size of vortex are generated. And as the flow further progresses, the turbulent cascade emerges. So the dynamics of turbulent flows are mainly described by the three main regime. So first one is the driving scale. At the scale, the energy is injected into the system. And the second one is the inertial range, where the nonlinear interactions are happening, which overcomes the dissipation. And at the last scale is the dissipation scale, where the energy is ultimately lost as the heat. So in the inertial range, the turbulent energy spectrum typically follows the power law scaling of k to the power minus 5/3, which is shown in the right-hand side image. And so figure B shows that the numerous experiments involve the turbulent flow, which includes the air and water. And when these fluctuations are plotted, on the plot of energy versus wave number, they all collapse into a single curve, which shows the universality of this scaling k to the power minus 5/3 in the inertial range. So interestingly, similar signatures are observed in the solar wind plasma turbulence also. And the plasma turbulence, which is very common in the universe, which is observed across vastly different scales and systems that include the fluid flow from the laboratory matter flow to various astronomical flow, which includes the solar wind, the magnetospheric plasma, then interstellar medium, and the galactic and intergalactic medium. So among these, solar wind provides one of the most accessible and the well-studied plasma turbulence. This is primarily because of the in-situ spacecraft observations are possible. So Huang et al. Used the data from the Parker Solar Probe mission from the multiple events to study the power spectral density of magnetic fluctuations. So they showed that within the inertial range of the turbulence, that means the frequency less than 1 Hz. In the graph, first vertical pink line shows the frequency corresponding to the ion cyclotron frequencies. So at the lower frequency, we observe the inertial range. The scaling is k to the power minus 5/3. And which shows that in the solar wind turbulence, the energy is mostly driven by the alpha waves at the large scale. but at the small scale, or scales comparable to the ion gyro radius or ion inertial length scale, which is denoted as the second and third vertical pink line, KDI equal to 1, where DI is the ion inertial length scale and rho I equal to ion gyro radius. So then at the scale comparable to the ion gyro radius, they showed that the magnetic field spectrum steepens significantly. The scaling is around minus 3.8, and at the scale smaller than the ion gyro radius, the scaling is around minus 2.63. But they also shows that this is the dominant peak value, but they shows that the slope value near the ion gyro radius shows the very large distribution. It is varies from minus 2 to minus 5. And this study is also reported from others, other study also and other spacecraft observation also. So this steepening is not, steepening of solar magnetic fluctuation at the small scale is not well understood. Mainly two types of fluctuation are proposed to understand this steepening. The one is the kinetic alpha waves, and second is the ion cyclotron waves. So our goal is to use the high resolution direct numerical simulation to observe these statistical features of depending upon the depending on Prandtl number and the different ion inertial length scales. So as I said that at small scale, the magnetic energy spectrum is steepened significantly due to the many kinetic effects, which includes the wave-particle interaction or the wave dispersion. And so as the MHD description of a plasma turbulence is consider the plasma as a single conducting fluid, which is valid up to the large scales only. But it begins to break down when we consider the scales which are comparable to ion inertial length scales, where the motion between the electron and ion begins to decouple. So to include the kinetic effects in our simulation, we need to keep the whole term in our MHD simulation, which account for the relative drift motion between electrons and ions. So three-dimensional Hall MHD equations are often used to study the astrophysical plasma turbulence, so it can capture both the fluid and kinetic scales. So these are the Hall MHD equations. First equation one is the momentum equation, which describes the evolution of the velocity field, which includes the convective acceleration plus pressure gradient plus the magnetic tension term and the viscous diffusion term, and the last one is the forcing term. Similarly, equation 2 is the describe the evolution of magnetic field, where del cross U cross B is the shows the advection of magnetic field by the fluid flow, and the di J cross B is the whole term, which is shown in red, and the eta del square B is the magnetic diffusion, and FB is the magnetic forcing term. And the third line shows the incompressibility condition of flow, and the del dot B represents the divergence-less nature of magnetic field. So here di is the ion inertial length scale, which we consider in our simulation, which is defined as the ratio of speed of light to the ion plasma frequency. So the whole term is generally written for the fast flow or at the higher frequencies. So then the pressure is, the total pressure includes the thermal pressure plus magnetic pressure. In the mu and eta are the kinematic viscosity and magnetic diffusivity respectively. And as we are studying the decaying turbulence, Fu and Fbr is 0 in our simulation. And the other two important parameters are kinetic Reynolds number, which gives the sense of a ratio of inertial forces to viscous dissipation. And another is the magnetic Reynolds number, which is important to understand the inertial forces to magnetic dissipation. And the ratio of these two parameters will give you the value of Prandtl number. It is defined as the ratio of kinematic viscosity to magnetic diffusivity. So we use the pseudospectral method, which allows us to efficiently compute the nonlinear terms which are present in our simulation using the fast Fourier transform. And we apply this in a fully periodic domain, fully triply periodic boundary condition used in a cubic domain with sides of length equal to 2 pi. And the time evolution of velocity field and magnetic field is done by the second order Adams-Bashforth integration scheme. And we ensure that all our resolution is fully resolved. That means the maximum wave number which are present in our simulation is greater than the dissipation wave number. So we perform total 8 simulations across the different resolution and different Prandtl numbers and different ion inertial length scale. So run 1, 2, run 3, and run 7 and 8 are the 512 cube resolution, while run 4, 5, and run 6 are the 1024 cube simulation. So we systematically vary the magnetic Prandtl numbers ranging from 0.1, 1, and 10. The reason behind choosing this value of Prandtl number is that in the many laboratory metal flow, at the core of planets, or we can say that at the core of planet and the solar corona, the range of magnetic Prandtl number is very small, of the order of 10 to minus 4 to minus 6. But in the interstellar medium or intergalactic medium, the range of Prandtl number is very large compared to 10. It is of the order 10 to 5 or up to 10 to 10 also. But that is not possible to achieve this value in the simulation because with the available computational resources. But so, and also we use the ion inertial length scale DI. In most of the run we use 0.05, but run 7 and 8 are at the higher ion inertial length scales. So here RE lambda is the Taylor microscale Reynolds number, which give you the sense of how turbulent the flow is. And tau c is the energy cascade completion time, which shows whichever energy which you injected in our system, it is completely transferred from the largest scale to the inertial scale. And the last two parameters shows the resolution of our simulation. They all are greater than or equal to 1, which shows that our resolution, all our simulation are resolved, all the scales. So the K maximum is 170 for 512 cube, and the both velocity and magnetic field are initialized by this of the form of k raised to 4 exponential minus 2k square. So here we shows the temporal evolution of the energy dissipation rate. The figure A is for kinetic energy dissipation rate, B is the magnetic energy dissipation rate. The peak in this plot shows the cascade completion time, which we have used to study the statistical properties at this time also. The figure C shows the ratio of kinetic to magnetic energy, and it increases further with time, which shows the dominance of magnetic energy over kinetic energy, and it also increases with Prandtl number because of the lower magnetic diffusivity at higher Prandtl numbers. So here we show the compensated kinetic and magnetic energy spectra in inertial range for run 4, 5, and 6, which are at the higher resolution. So they all follow the Kolmogorov scaling of k to the power 5 by 3, which is shown by the solid black line. So we can say that it is independent of the Prandtl number we have considered in the simulation. But the second inertial scaling is richer because it depends on the Prandtl number. So here the dashed line shows the boundary between the inertial scale and the second inertial scale. Or we can say the ion inertial length scale. So for in the simulation at Prandtl number 0.1, the kinetic energy spectra goes like k to the power minus 11 by 3, the red curve from figure A. And whereas high Prandtl number 1 and 10, this spectra varying as k to the power minus 17 by 3, were blue and black curves. And the figure B is for the compensated magnetic energy spectra. So for Prandtl number 0.1, lower Prandtl number, the magnetic energy spectra goes like k to the power minus 17 by 3, but at higher Prandtl number, it goes like k to the power minus 11 by 3. So to understand this scaling behavior, we provide the theoretical arguments based on the dimensional analysis of equation. So comparing the energy transfer time by the whole term, di del cross j cross b, and the kinetic energy transfer time by u dot del u. So it leads to the ratio of magnetic to kinetic energy varies as 1 by di k whole square. We call it the ion cyclotron waves. And at higher Prandtl number, we compare the energy transfer time with the magnetic field and the magnetic tension term of kinetic velocity field equation. So we got the ratio equal to di into k whole square, and we call it the Whistler waves. So further to understand this ratio, we plot the Alfvén ratio, EB by U versus K. So we can see that at K greater than Ki, the Alfvén ratio varies as K to the power 2 in the high Prandtl number simulation for blue and black curve, but whereas it got like K to the power minus 2 in low Prandtl number simulation. So using this slope value, we can calculate the scaling exponent for magnetic energy or kinetic energy, which we observed in our previous slide. So although the observed slopes in Alfvén ratio and scalings in kinematic energy spectra are very consistent with each other, although the scale which are available in our DNS are very limited. So further, we have used the concept of magnetic polarization to understand the scaling behavior of scaling exponent. So here magnetic polarization PM is defined as the sigma n times sigma c, where sigma is the normalized magnetic helicity, which is defined by equation number 5. Sigma c is the normalized cross helicity, which is defined by equation C. So this magnetic polarization parameters characterize the different wave that the Hall imagery system supports. So if PM equal to +1, that correspond to left-handed polarization ion cyclotron waves, and the PM equal to -1 correspond to ion Whistler waves corresponding to right-handed polarization. So using this formula, we have calculated the left and right fluctuation spectra and the magnetic energy spectra. So here we plot the L and R fluctuation from run 1 and 2 and 3. So figure A is for Prandtl number 1. So you can see the blue solid line is for the L fluctuation, ion cyclotron wave. So and red dashed line is for the Whistler wave. So the trend reveals that the chiral symmetry breaking is observed in our all simulation because of Hall effects. And the trend indicates that the R fluctuation dominate over the L counterparts, at the Prandtl number greater than or equal to 1. But the lower Prandtl number, we observe the L fluctuation dominant over the R fluctuation, which is clearly visible in our figures. Here we shown the compensated magnetic energy spectra for left and right fluctuation. So for lower Prandtl number, we observed for both L and R fluctuation, so the scaling exponent nearly 17/3, at higher Prandtl number 11/3, and sees the 11/3, which is observed in the unpolarized magnetic energy spectra also. So we can say that both spectra are consistent with each other. Similarly, we have shown for the run 4, 5, and 6, which are at higher resolution. So here one key observation is that at lower Prandtl number, the difference between the R and L fluctuation is reduced compared to figure B and C. So the exact value of Prandtl number at which the R fluctuation gives the way to dominance of L fluctuation, it depends on the resolution also. The scaling exponent is the same as the previous one we observed. So our observation about the L and R fluctuation are clearly visible in run 7 and 8, which are performed at the higher inertial length scale. So here the DI equal to 0.1. So in figure 1, that is at Prandtl number 0.1, but DI equal to 0.1. The clear dominance of L fluctuation is observed over the R fluctuation, which we have shown in the alpha ratio. And at B figure, we have shown the R fluctuation, that is red dashed line shows the clear dominance of R fluctuation over L fluctuation, and the scaling exponent which are the same as the previous one. Furthermore, we have calculated the investigate intermittency in decaying 3-dimensional high-energy turbulence at the tau c time. It is defined as the difference between the two variables separated by distance L. So here we shown the PDFs of the velocity field increment for run 4 and run 5 and then 6. So, and here the black curve is for the comparison. This is a Gaussian PDFs. So as you can see that the large scale, which are shown by the green dashed dot line and blue dash line or pink dash line, they are nearly Gaussian. So we can say the large scale deviation is very small, but the small scale deviation is very high, which is observed in all our simulation. That is denoted by red solid line and blue dotted curve. Although the PDF of velocity field increment is highly suppressed at the higher Prandtl number, we can see in figure C, that is deviation is less for small scale. Similarly, we saw for the magnetic field. So here we observe the similar trend for the large scale. That large scale is nearly Gaussian, but for small scale, we observe the opposite trend. At the intermittency in magnetic field increases at the higher Prandtl number, which shows the multi-factor nature of magnetic field at higher Prandtl number. And further, we quantify the intermittency by structure function, which are defined by equation number 7 and 8. So the structure function is the linear function of different order P. So if the structure function varies linearly with different order P, we can say that turbulence is monoscaling, and if it is non-linear, we can say that it is a multi-factor behavior. So we use the ESS plot, which provide the extended range. So you can calculate we can calculate the best slope value from the longer range available in our simulation. So here,
Please summarize.
Yes, sir. So here in top panel, the blue dashed line is for the magnetic field and the red dashed line for velocity field. So you can see that at a higher Prandtl number, the deviation of blue line is increases, which again says that the intermittency is increases in magnetic field at higher Prandtl number, but the deviation of red line, which is for the velocity field inertial range, it is suppressed at the higher Prandtl number. And here we shows in the second inertial region, we shows the exponent ratio for the magnetic field. And here we again observe the higher intermittency for magnetic field at higher Prandtl number, which shows the multi-factor behavior of magnetic field. And it is suppressed at the lower Prandtl number. So to summarize, so we have the both kinetic and magnetic energy spectra in inertial range follow the K41 exponent, which is independent of Prandtl number we have considered in the simulation. But the spectral exponent at spectral exponent, which is K to the power minus 17/3 and 11/3 for magnetic energy spectra in sub-inertial region, respectively for low and high Prandtl number simulation, are described based on ion cyclotron waves and Whistler waves, but supported by the incompressible Hall energy system. So intermittency and multi-factor nature of magnetic field in the inertial region and sub-inertial region at high Prandtl number increases, which is I have described based on the PDFs of longitudinal field increments and the structure function. So these are the references and this acknowledgement. Okay, thank you.
Thank you. Questions? So if there are no more questions, let's thank Pratik and all the speakers from this session. So I request all the speakers from this session to come on this stage.
This is the end of the session 2, and now I request our session chair, Dr. Amit Shukla, to come on the stage and present a memento to our session speaker, Dr. Durgesh Tripathi. Sir, please come on the stage. I also invite Dr. Nishan Sese to present a memento to Dr. Amit Shukla, our session chair. Now I request all oral talk presenter of this session to please come on the stage for the session group photograph. Thank you, all of you. We now move into the poster session 1. Accompanied by the high tea in the lobby, poster presenters are requested to stand by their display and interact with the evaluator and audience. Please note this is the important part of our curriculum and will contribute to award decision and everything. So now for the time for the poster session 1.